Hello, good evening my students. My name is Dr. Nagaraj Sitaram. I am Principal and Professor at Amrita Institute of Engineering, Biddi. I would like to welcome you to the class of Fluid Mechanics. We will be covering the module 1 today. In this module we have fluid and their properties and fluid pressure and its measurement. I would like to tell you very important thing. The fluid mechanics module 1 covers the properties of fluid, which actually helps us to identify fluid. The learning outcome is student will learn the fundamental properties of fluids and its applications, and at the same time you will also learn the hydrostatic laws and application to practical problems solving. The sequence of lecture is like this. We will first explain the concept of fluid, system of units, fluid properties, both the theory and problems. We will describe mass density, specific weight, specific gravity, specific volume, viscosity, cohesion and adhesion, surface tension and capillarity, compressibility and bulk modulus, excess pressure, inside water droplet, soap bubbles, and we will cover the problems in that. Now, before I continue, I would like to tell you very clearly, a fluid can be defined as a substance which can deform continuously when being subjected to shear stress at any magnitude. It can be a very small one or it can be a very big one also. In other words, it can flow continuously. You may be wondering what I am talking. Mind it well, the clouds movement you have seen, it flows. Water movement you see, it flows. Even a solid particles, they also flow. A fluid, it includes any liquid or gas. Hence, a fluid is any substance which flows because its particles are not rigidly attached to one another. Examples of typical fluid used in engineering applications are water, oil, air, petrol, oxygen. Now, before I could continue, I would like to show you the applications of fluid mechanics. You can see the animation behind a wake, you can see chemical mixing in a stirrer, you can also see a movement of a ship, you can also see the aeroplane and a person who is swimming, and in the last photograph you can see a dam and the stress variation in the dam. It means the application is enormous, starting from the smoke pollution, starting from the sewage flow, starting from the river flow, gas flow, aerodynamics, helicopter, even say NASA satellites, whatever you say, whatever flows, application is enormous. Now, further I would like to tell fluids, when we talk about the gases and the liquids, it can be in the two forms. It can be statics as well as dynamics. I will give an example. You can see here a glass is having a water and it is in a static condition. It means the velocity is 0. You may be thinking why I am showing this. You can visualize the same thing when you are near a petrol bunk. The bunker is having the petrol, static condition. You may see a overhead tank, there are also static condition. A oil tanker also, which is not moving, is under static condition. We would like to know the properties of these under static condition. At the same time, you can see when the flow is taking place in various system, maybe a AC duct, maybe a pipe flow, maybe a river flow, or many more. It means we would like to analyze the flow characteristics based on the velocity is 0, which is called statics, and velocity is not 0, we call dynamics. Naturally, dynamics will be more complicated as the statics, right. Now, we will continue further. Let us see the three parts of the system, that is a solid, a liquid and a gas. You can see in the slide, the solid is having the molecules very nicely tied to each other. You can see in the form of a spring as shown. In the liquid also you can see it is slightly loose, it is not that tight as compared to solid. but also you can see in the gaseous state it is fully free, open to atmosphere. So, the molecules are fully loose, correct. Again repeat, you can see the solid particles, you can say anything, any duster or any material, it is all very closely packed, but if you see the liquid, it is slightly loosely packed, right. And third one, the gaseous state is the most loosely packed. After this, we can say when a shear stress is applied, the fluids continuously deform. When a shear stress is applied, the fluids continuously deform. Solid, deform or bend. You may be thinking, what is the shear stress? Let me illustrate you. Now this is a body. If I apply a force in this direction, normal direction, it is called normal force. It is not a shear force, my dear friends. It is a normal force. We always take the area of this gentleman and this force, which is calculated as pressure. But if I apply a force tangential to this on the top, it is called shear force. I repeat, the shear force is on the top and the normal force is exactly perpendicular to the area. So, this is the difference between the shear and the normal force. Same thing is applied in the diagram. You can see the solid can be also applied a shear, a fluid can also apply shear, but solid will not deform that much. Shear force will deform more the fluid motion, right. Behavior of a solid and fluid are totally different. Under the action of a constant shear force, the solid will not deform much, but a liquid or a gas will flow like anything. So, deformation or you can say disturbance will be very high in the liquids. So, is it clear? Now, very clearly I am showing two diagrams. You can see in one case it is a static glass on which the ball is resting, that is a static condition, and other one smoke is coming, you can see the turbulence of the smoke in that. Now, let us continue our discussion in difference between liquids and gas. Liquid on the one side is difficult to compress. I am not saying it is incompressible. It can be compressed, but we have to apply a very large force. But gases, you know very well, in a piston and all, when we compress it, it will compress very nicely in our automobiles. Changes of volume is large, cannot normally be neglected and are related to temperature. But liquid, you can say practically it is incompressible. So, my dear students, mind it well, we are differentiating between liquid and the gas, which is actually the fluid, you can say. Now, one more advantage of liquid is it occupies a fixed volume. You can see I have put a water in this case, it has occupied the same cylindrical portion, right. Suppose if I put a rectangular container, it will occupy the same. So, definitely you can say that liquid occupies a fixed volume, but you can see also here above this particular level where the water level is seen, it is fully air. So, no fixed volume, whatever volume is there, it is totally filled up there. So, that is the thing. And one more thing, you can see in the same example, a free surface is observed in liquid. You can see a water is there and there is a free surface, right. But if I empty this fully, it will be fully filled with the gas molecules. It means we can say in the gases, it completely fill the vessel, so that no free surface is formed. So, one thing is very clear, that liquid is incompressible relatively, gases can be compressible. At the same time, liquid occupies a fixed volume, which I have shown through the example, and gases no fixed volume. At the same time, liquid, a free surface is observed, whether it is a oil, whether it is a milk, whether it is a water or anything, it will, you can see a free surface horizontal, right. At the same time, in the gases, it completely fills the vessel, so that no free surface is formed. I am very sure my students have followed what is the difference between liquid and gas. Let us see one more part of it. Whenever we are talking about units, we need to discuss about the system of units. You may be thinking why I am discussing. We have a SI system of units which we follow all universe. In fluid mechanics, we must describe various fluid characteristics in terms of certain basic quantities, such as length, we say L, time, T, and mass m. Indirectly we also say MLT system, they are all primary dimensions. I repeat, my dear students, in fluid mechanics we must describe various fluid characteristics in terms of certain basic quantities such as length L, time T, mass m. A dimension is the measure by which a physical variable is expressed qualitatively. That is, length is a dimension associated with distance, width, height, displacement, etc. Similarly, we have basic dimensions mass m, temperature theta, time t in seconds. We can derive any secondary quantity. You may be thinking, why I am talking about secondary? We just now told, my dear students, primary quantities are m, L, t, theta. What I mean is mass, length, time and temperature. Secondary quantities means these are the quantities which are derived based on primary quantities. Do you understand? I repeat, secondary quantity means these are the quantities which are derived based on the primary quantities. It means, for example, force is equal to, you know very well, mass into acceleration, right? Force is equal to ma, you call it, right? M stands for mass, so we say m. You can see F is equal to m. Acceleration is nothing but rate of change of velocity, L by t square. In that case, the dimension becomes F is equal to m into L into t to power minus 2. It means MLT, they are the basic quantities, and F is equal to MLT minus 2. It means it is a secondary quantity. So, it means any characteristics of fluid which we may be discussing now onwards can be described based on the primary quantity terms, that is MLT theta, or it can be derived from the secondary quantity in the form of MLT combined, right. We go ahead. System of units can vary from country to country. I think earlier we were ruled by Britishers people, they used to use feet, pound, inch, then the MKS came, then SI system came. So, system of units can vary from country to country, but dimensions do not. We continue. Before I continue, I would like to show the primary unit mass as m, the SI unit is kilogram, mass is m, SI unit is kilogram, length is L, always measured in meters, length is L, always measured in meters, time is T, seconds S, temperature is theta, Kelvin K, temperature is theta, Kelvin K, current is I, ampere is the measurement, current is I, ampere is the measurement, luminous intensity is candela and is measured in CD, force F, though no doubt it is a dependable quantity, but we measure it in newtons. So, these are the system of units and dimension where we measure the mass in kg, length in meter, time in seconds, and it goes on. So, is it okay? So far we have discussed about the primary quantity and the secondary quantity, and we have also mentioned which are the important SI units which we are going to use. Let us continue our discussion. Earlier, as I mentioned, from country to country it used to vary. You can see in the CGS, instead of length meter, they used to measure in centimeter. In the force, they used to measure in Dian. Mass kg, it was in gram, and time in seconds same, and pressure in SI system we measure in Pascal, which is defined as Newton per meter square. I repeat, the pressure in SI system is defined as Pascal, unit is Newton per meter square, but if you go to CGS system, it becomes Dien's per centimeter square. My dear friends, if you go to the English system, the length is measured in inch. In civil engineering, still we use this FPS system. Most of the people, they talk about their site 60 feet by 40 feet, etc. Force in pound, mass in slug, time in seconds, and pressure in PSI. Very interesting PSI. Why I am telling? Because all are you are having two-wheeler or four-wheeler, right? Whenever you go to a petrol bunk, you see the dial 26, 28, 30 or whatever number is there, it is a pounds per square inch. It means till today, this is 2016, in all our petrol pumps we are using English units to measure the tire pressure, right. So, definitely this particular slide gives you a comparison between system of units SI, CGS and English. Is it okay? Let us go further in the same. Let us take an example as a kinematical equation for the velocity. You know very famous law, V is equal to V naught plus AT. Some people say V is equal to U plus AT. Now, this equation has got a left hand side, we say LHS, and this equation has got a right hand side, I designate as RHS. I repeat, this is a simple equation of velocity. V is equal to V0 plus acceleration into time. It has got two parts, one is left hand side, other one is right hand side. Left hand side dimension, if you see velocity, my dear friends, you know it is a meters per second. I repeat, velocity is meters per second. It means length upon time, right. Meters per second, meter length, time t. So, L by t. So, LHS, if you see, the dimension is coming L by t, or you can say LT minus 1. Is it okay? Now, let us see what happens to the right hand side of the equation. The right hand of the equation is V0 plus AT. V0 is same as velocity, we have no dispute, it will remain as L by t. A stands for acceleration, acceleration is L by t square, that you can see in the slide, and t is the time, which is nothing but time, L into t. So, L by t square into t, it cancels, again you regain L by t. It means this equation is dimensionally homogeneous, right. It means this equation, whatever dimension we are getting on the left hand side, which is meters per second, on the right hand side also I am getting same meters per second. So, it is a dimensionally homogeneous. The same thing has been represented in the second bullet. You can see that where V0 is the initial velocity, same L by t, my dear friends, and A stands for the acceleration, L by t square, and T stands for time interval, that is t, capital T. So, in terms of dimensions of the equation, we can expand it as on the left hand side, as I mentioned, LT minus 1, and on the right hand side you can see again LT minus 1 for V0, acceleration LT minus 2 into T. It means I am trying to see whether the dimensions, primary dimensions of the equation on the left hand side LHS is same as that of right hand side, and I am finding it true. So, my dear friends, we call it, this equation is dimensionally homogeneous, both sides units are same. Is it okay? Let us go to the one more concept of fluid, which is a fluid continuum. You may be seeing a graph in which on the y axis you have variation of mass with volume, on the x axis you can see a volume. Normally, if you see a fluid particle like in a glass, you can say the fluid molecules will be one by one. You can see in the inside lot of molecules are there. So, no doubt they are slightly different apart, correct, some gap is there. When we consider the fluid, whether it is a gas or a liquid, we assume that the molecular gap is not coming. I repeat, my dear friends, the fluid continuum concept says continuity of molecules. I repeat, fluid continuum concept is continuity of molecules. In this glass, whatever water is there, the molecules are continuous, there is no gap between any two molecules, whether it is a liquid or whether it is a gas. This concept is known as fluid continuum, right. Now, you can see, treat the fluid as a continuum, assume that all the fluid characteristics vary continuously throughout the fluid. Is it okay? So, my dear students, I understand that you have understood the concept that the fluid continuously coming one after the other, there is no discontinuity of molecule, correct. That is called fluid continuum. Is it okay? Now I go to the first property, which is very important to describe. Now one thing I would like to tell you, the fluid properties, which is actually unit 1 or you can say module 1, we need to identify some characteristics of the fluid based on which I can describe this liquid is say water, this liquid is a milk, this liquid is a mercury, or this is a air gas, this is a helium gas, like that. What are those properties based on which we can say it is going to be important? So I define the first property, fluid mass density, or we can say mass density. It is represented by rho. M subscript stands for mass. Repeat, rho m. Rho means density, m subscript is for mass. Density is defined as mass per unit volume. You may be thinking what I am talking. Let us take the same example. This particular glass has got water. It has got some mass in that. Say assume that this is say 100. Suppose if I replace it by oil, it will be 80. Suppose if I replace it by mercury, it will be further heavier. It means the volume is same, mass is varying. Definitely the unit becomes kg per meter cube. For a given volume, I repeat, for a given volume, what is the weight it is occupying? What is the weight it is going to weigh? Suppose if I put any lighter liquid, say gas, it will be very light, right. If I put mercury, it is very heavy, and if I put water, it is slightly better. But if I put petrol, you know very well, petrol density is hardly 686, right. So definitely it is lighter. So it is the first property based on which we can characterize, we can differentiate different liquids and gases. We call it mass density. We can say it is the mass per unit volume, right. Let us further describe this. Dimensions of mass density is kg per meter cube. You know very well, my dear friends, it is a mass per unit volume. Mass is measured in kg. I repeat, density has a units of kg per meter cube. You can see the formula, rho m is equal to m by v. M stands for mass, which is in SI kg. Volume is a volume of a say room or anything, meter cube. So definitely the mass density dimensions are m l minus 3. Now one more thing I would like to tell you very clearly, the density is the first important characteristics for liquid to describe. What happens when the temperature is more? You may be taking hot water bath, no, and I am taking say cold water bath. Which is more denser? Question is that, right. It all depends upon the molecular motion. If you heat the molecule for liquid, it is going apart, so density will decrease. It means hot water will be lighter density wise and cold water will be heavier density wise. Mind it well, these are all very important for lubrication purpose, correct. So again repeat, if I take density as characteristics, if density of liquid at 20 degrees centigrade is 1000 kg per meter cube, say for water. If I take density of water at 60 degrees centigrade, the value will be somewhere around 990 or 991 kg per meter cube. It will be lighter. So mind it well, it is a function of temperature. That is one thing. Number 2, in case of fluids, as the pressure increases, volume decreases, hence mass density increases. You are packing the molecules, so it is going to increase. Now let us talk about one important thing. What are the typical value for abundant water and abundant air? You have two fluids which are near to you. Always we drink water and we breathe air, correct. So air you can see is around 1.23 only kg per meter cube, but as far as the water is concerned, it is 1000. It means 100,000 log scale away. Mind it well, they are totally apart, right. So mind it, the water density is 1000, air density is 1.23 only, and if you take the mercury, it is 13.6 into 1000 kg per meter cube. So, density becomes one of the first characteristics to define the liquid. Is it okay? Shall I go ahead? Now, let us say one more thing. You have defined density. Suppose I am not interested in mass per unit volume. You know, gravity is there everywhere. I would like to know what is the weight per unit volume. What is the weight per unit volume? For example, you go, I can ask you what is your weight, I will not ask your mass. You can say I am 60 kg sir, 70 kg sir. It is the weight which is very easily measurable. So, for that we have defined another property called specific weight, and or we can say it is a weight density. It means I would like to know, in the same glass bottle you can see, instead of talking about the mass about this volume, I will be talking about the weight, how it weighs, correct. Suppose if it is a petrol, it will be weighing lesser. Suppose it is a water, it will be weighing slightly more, and suppose the whole thing is filled with mercury, it will be weighing very heavily. I will feel the weight on my hand, correct. So, now weight density, or we can say specific weight, becomes the second parameter to describe the property of the liquid. Let us see how it goes. The weight density or specific weight of a fluid is the weight per unit volume. It means weight is measured in newtons and volume is measured in meter cube. So, unit will become Newton per meter cube. Is it okay? I repeat, the weight density or specific weight of any fluid, maybe gas, maybe liquid, maybe water, maybe carbon tetrachloride, maybe benzene, petrol, whatever you ask, the weight per unit volume is unit is Newton per meter cube or Nm minus 3. With the increase in temperature, the effect is remain the same. Volume increases, hence the specific weight decreases as our density was decreasing, correct. I repeat, the specific weight of the liquid decreases as the temperature increases, and vice versa is true. At the same time, the relationship between specific weight and mass density is described by a simple relationship. You have seen specific weight is the weight per unit volume, density is the mass per unit volume. Definitely gamma W or gamma is related with rho m into g, that is g is the acceleration due to gravity. The value is, I think you know very well, it is 9.81 meter per second square. So, mind it well. Now, we have described two parameters, number one the density, mass density, and second one is specific weight. They are connected by nothing other than gamma is equal to rho m into g, where gamma stands for weight per unit volume, that is Newton per meter cube. Rho m stands for density, which is nothing but kg per meter cube into acceleration due to gravity, which is 9.81 and standard value. I think I have mentioned about the specific weight of the water, its value is 9623.61 Newton per meter cube. Now, let us take the third important property, which we call it specific gravity. Now, we have a tendency to compare, okay, do not mistake me, we have a tendency to compare. I would like to compare two liquid, say air here and water with me, or liquid here and petrol here. I would like to compare. Then question arises, which is the standard liquid? Normally we take water as the standard. Water is the standard because it is available in abundant, number one. Number two, we want to compare the specific gravity of oil with reference to water. It means specific gravity is also known as relative density. I will come to that very slowly. The relative density means I am comparing two liquids. I said density of the fluid on the top and density of the standard fluid on the down. Means if I take water, it will be in the down, density of the kerosene will be on the top, density of the water will be down, density of oil will be on the top, density of water will be in the down. Value is less than 1, you can see very clearly. Let us come back to our slide. You can see here the specific gravity is a very important term. it is called relative density. It is defined as the ratio of the density of a substance or a liquid to the density of some standard substance at a specified temperature. Let us say density of mercury divided by density of water. Density of mercury is very heavy, it is 13.6 into 1000, and density of water is 1000. 1000 cancels here. You can see here on the right side, mercury is 13.6. Water, you cannot comparing water to water, it is 1. Oil is lighter, 0.6 to 0.8. You may be thinking why I am talking all these things. Mind it, my friends, when you are going to pour one liquid over the other, example, you can say here itself, water is here and air is on the top. Air cannot be down. Heavier the liquid, it will occupy the lower position. For example, if I put a mercury in this, it will occupy this position, bottom, and over which water will be there, over which oil will be there. Is it understood? Shall I repeat? I repeat again. You can see, suppose if I pour mercury, suppose if I pour water, and suppose if I put any oil in this, oil will occupy the top position being the lighter, correct? Next will be the water, which will be occupying the second position, and the mercury will be the heaviest, it is going to the bottom. So, mind it well, higher the specific gravity, lower is the position. Repeat, higher the specific gravity, lower is the position, lighter is the specific gravity, upper is the position. Is it okay? So, this is what the importance of specific gravity. So far we have discussed 3 important parameters. One is the density, mass density, next is specific weight, and then we have gone to specific gravity. These are the 3 important things where you will find to describe how this density will be varying from one liquid to other liquid, and how we are going to compare it with a parameter called specific gravity. Then you may be wondering, I have not talked about the units of specific gravity. My dear friends, it is a ratio of the 2 density. I repeat, there is no unit for specific gravity, it is a unitless quantity. I repeat, specific gravity has got no unit, because it is the density of the fluid divided by density of the standard fluid. So, both will cancel, there is no, it is only a dimension number, 13.6, 12.2, 1.65, 0.6, 0.8, etc., etc. Is it okay? Let us go to the next one. Now, we come across one more interesting term, it is called specific volume. Specific volume as defined, it is the volume per unit mass. Then you may be thinking, sir, just now you told me density is mass upon volume, correct? Mass per unit volume. Specific volume is opposite of that. I repeat, the specific volume is 1 by density. It means it is the volume per unit mass. It is the volume per unit mass. Mind it well, it is opposite to the density. So, specific volume is nothing but it is the volume per unit mass. In this case, if temperature increases, specific volume will also increase, because density decreases. You remember, I told you, no, hot water will be lighter and cold water will be heavier, but in this case specific volume, if you ask me, specific volume of hot water will be more and cold water will be less. Is it okay? I hope you understood this important concept of specific volume. As the pressure increases, volume decreases and specific volume will decrease. It is exactly the reverse effect of the density, correct? It is exactly the reverse effect of the density, or I can say specific volume is nothing but 1 by density. Take care. Next comes here, for water specific volume is 0.001. You may be thinking how I got this answer. It is very easy, my dear student. The density of water is 1000 kg per meter cube. I repeat, 1000 kg per meter cube. You reverse 1 by 1000, it will become 0.001. So, that much volume it is going to occupy per kg. Is it okay? So, I am very sure that you have understood so far the density, mass density, specific weight, then specific gravity, and now just now I told you about specific volume, which is nothing but 1 by density. Let us go to the next one. Now we come to a very interesting situation. You can see the slide video also. You can see here a ball is falling and is splashing. In other one it is not splashing much. You can see very clearly in the video it is splashing a lot, and in one case it may not be splashing much. What is this actually, this behavior called? This behavior is known as viscosity. We say fluid friction. For example, as I told you, when we apply a shear force, the fluid is deforming, correct? When I apply a shear force, fluid is deforming. What is the rate of deformation? Suppose if I take honey and it deform, you agree with me that it will not deform much. If I take mercury and apply shear force, it will not deform much. But if I apply same thing to water, it is going to deform a lot. If I apply to air, it is going to deform a lot. Definitely there is a certain thing which is actually coming between the two layers. This layer called fluid friction, which is known as the viscosity. Let us see the flow of real fluids exhibit viscous effect. Then you may be thinking, sir, whether what is the ideal fluid? Ideal fluid is a fluid which has got zero viscosity. I repeat again, my dear friends, the ideal fluid is a fluid which has got zero viscosity. It need not apply any shear force. You need to apply a shear force in this glass bottle to move the water, but for an ideal fluid you need not apply anything, it will move like that only. So that is called inviscid, which means viscosity is zero, no resistance to flow, that is the ideal. Then you may be thinking, what is the opposite of that? Maximum resistance to flow is a solid. Whatever you deform, try this glass, I am deforming, it is not deforming at all, I am applying shear, it will break but it will not deflect, correct? So it means that it is totally solid, there is no variation or there is no deflection in this, it may break. Mind it well, zero viscosity is a ideal fluid and maximum viscosity is a solid. Now let us come to the viscosity is a property of fluid which offers resistance to deformation as mentioned in the slide. It is mainly due to cohesion and interaction between molecules. I will describe this later. It is mainly due to cohesion and interaction between molecules. Different fluids deform at different rates under the same shear stress. The best example is air, you will deform very fast, for water bit less, mercury very less. Fluid with a high viscosity such as syrup, you may be drinking syrup, you are not well that time, deforms more slowly than the fluid with a low viscosity such as water. Now you may be thinking whether this viscosity is related to the flowability. Answer is yes. More the viscous liquid, the flowability will be less. I repeat, the viscosity is the resistance offered by a fluid, maybe gas, maybe liquid, to flow. Higher the resistance, flow will be less, honey. Lesser the resistance, flow will be more, water, correct? I will give one more imagination if you can have. You put one bucket of water and one bucket of honey and try to throw it. What will happen? Water will spread like anything, correct? But honey will not spread like anything because it has got more viscosity. It will oppose to the flow. Water relatively less viscous, it will flow like anything. Air is everywhere, I did not tell anything. So this is what the viscosity is there. Let us see one more thing. Examples of highly viscous liquid, tar you might have seen, tar they will heat and then put on the road. Molasses, the cane sugar molasses, that is also equally important. Now about the gases, transfer of molecular momentum is very important in this. Molecules play a big role. Viscosity increases in gases as temperature increases. Why? You may be thinking, because if you heat a gas, it will, the violence of motion is very high. So viscosity increases as temperature increases, viscosity increases as pressure increases. This is what the effect is. For liquids, cohesion and momentum transfer, viscosity increases as pressure increases, same thing, but viscosity decreases as temperature increases. I told you already the density of the liquid is decreasing as temperature is increasing. So, viscosity is decreasing as temperature increasing. So, mind it well, these are all very important. Gases, transfer of molecular momentum, liquids, cohesion and momentum transfer. We will see this more in cohesion and adhesion. Relatively independent of pressure, you can say for the liquids, you can say it is incompressible, we say. No doubt it is compressible to some extent, but not up to that extent. Now, let us see a small example. Viscosity, you can see, you can visualize this what I have shown as a river, a fixed wall on the bottom, a river bottom and moving wall on the top, it is moving. So, you can see this is V0 and velocity here is 0. You can see the velocity distribution is linear, it can be non-linear also. It means the velocity in any Kaveri river or any Narmada river, any river, maximum velocity you will find on the top, minimum will be at the bottom. So, maximum resistance is offered at the bottom where the wall is fixed, correct. I repeat, the maximum resistance is offered at the bottom when the wall is fixed and minimum resistance is offered on the top layer when it is flowing. You might have seen river flow, same concept is being applied. We say shear stress is proportional to shear strain. The shear stress is nothing but tau, shear strain is the dV by dy, dV stands for change in velocity, dy stands for change in depth. So, I would like to know this y is equal to mx. What is y? Tau. M is mu, viscosity, x. Then you may be wondering, sir, viscosity equation for an ideal liquid is 0. Answer is 0. Tau will be 0. We need not apply any shear force, it will flow like anything because mu is 0. Mind it well, tau is equal to mu into dV by dy represents a very important equation. It is called Newton's law of viscosity. He is the first person who has related the shear stress to the shear strain, and he has said the shear stress by shear strain is equal to a constant which is called coefficient of dynamic viscosity. Coefficient of dynamic viscosity. It means shear stress and strain are related with a law which is called Newton's law of viscosity. So, we will discuss this further also. Before that, I would like to show a small video on you. You can see the video will tell you, this is a video you can see in the capillary the water is coming or any colored liquid is coming. Suppose if I put colored liquid lighter here and heavier on the right side, you can see on the right side the liquid is not at all flowing, it is more viscous, and on the left side you can see it is flowing very fast. In the middle you can see it is in between. So, definitely the flowability is connected to viscosity, is it not? I repeat again, my dear friends, you can see again it is flowing very fast, maybe water or lighter liquid, but on the right hand side the other liquids are heavier, it is not flowing that fast. So, it says that the more viscous the liquid, the flow will be at less rate. Mind it well, it is governed by nothing less than that Newton's law of viscosity. The formula is tau is equal to mu into du by dy. Tau stands for shear stress, mu stands for dynamic viscosity and du by dy stands for, you can say, shear rate. Let us see one more video. This is also another video in which I have put a heavier liquid and a lighter liquid into two systems, right. We would like to know, suppose if I take this glass and I put two layers of liquid, and suppose if I move here and there, how it moves, that is the question. You can see here these are two layers of liquid, heavier liquid is here, lighter is here, and I am going to inject a dye. You can see very clearly the dye is being injected on a lighter side, and what I will do, I am going to twist it like this. Okay, you can see the deformation, the lighter liquid was on the top, heavier liquid is in the bottom. Can you see that, my dear friends? You can see the deformation is more in the lighter as compared to the heavier, and at the same time you can see the immiscibility of the two liquid. What do you mean by immiscibility? Heavier liquid is in the bottom, lighter liquid is on the top. I am giving a small motion in the beaker. You can see the beaker very clearly in the diagram. and you can see the deformation is taking place accordingly. So, the heavier liquid is moving in the bottom side and the lighter liquid is on the top side. So, this video also shows how the variation of viscosity affects the flowability. Higher the viscosity, you are right, low will be the flowability, and lower the viscosity, it will be the higher the flowability. Now, this is very important part. Can I describe the liquids or the fluids based on the Newton's law of viscosity? I repeat again, can I classify the liquids based on the Newton's law of viscosity? Now, you can see one graph. I told you, no, on the right side, on the x axis you have deformation du by dy, on the y axis you have shear stress, and I have shown here as a ideal fluid, and there is a Newtonian liquid. Can you see that, my dear friends? Tau is equal to mu into du by dy, which is nothing but y is equal to mx. Repeat, y is equal to mx is a line which is passing through origin. You can see the origin is there is no intercept. Y axis is the shear stress, x is the du by dy, tau is equal to mu into du by dy. It means there are some liquids, there are some gases which follow the Newton's law of viscosity. I repeat, there are some liquids, there are some gases which follow the tau is equal to mu into du by dy. We call them or we name them Newtonian fluids. Repeat, the liquids which follow Newton's law of viscosity, tau is equal to mu into du by dy, it is called Newtonian liquid. Then you may be thinking the other side. If the liquid or the gas is not following this equation, it may be dilatant, it may be pseudoplastic, it may be Bingham plastic, they are called as non-Newtonian liquid. I repeat, this is a very important classification. If a liquid or a gas follows the Newton's law of viscosity, we say it is Newtonian liquid. We say Newtonian liquid. If it is not following the other side, it is called non-Newtonian liquid. Maybe you may be thinking again, which are the non-Newtonian liquids and which are the Newtonian liquids. For example, Newtonian liquids are air, water, oil, all they follow. But on the other side, non-Newtonian, our own blood is a non-Newtonian liquid. Sewage, you may be pumping sewage, or heavy water, they are all non-Newtonian liquid. Definitely very important concept we have learned today, that the liquid which follow the Newtonian liquid follows the Newton's law, and non-Newtonian follows the non-Newton law. So, if you say in SI system the viscosity dimension is known as Newton second per meter square, in CGS system we call it Poise or Dian second per centimeter square. There is one more term called Centipoise. Centipoise is defined as 10 to power minus 2 or 1 by 100. I think I am telling you very smallly. You know very well milli 1 by 1000, 1 by 10, mm 1 by 1000, centipoise 1 by 100, micro 10 to power minus 6, nano 10 to power minus 9, mega 10 to power 6, giga 10 to power 9, like that it goes. So, we are going to use these units in the CGS unit of viscosity, which we have discussed in the Newton's law of viscosity, that mu value formula tau is equal to mu into du by dy, that is actually centipoise we measure in the CGS unit, and it is 1 by 100th of a poise. Poise is a CGS unit, while SI system it is called dynamic viscosity, it is Newton second per meter square. Inviscid flow means the effect of viscosity or negligible, it is a ideal fluid. You can see here a velocity distribution in which in the lower one we have a honey flowing, on the top one we can see water is flowing. Honey is more viscous, you can see the deformation in that, it is like a parabola, and in the water you can see it is almost like a straight, it behaves like a ideal fluid. So, water we can say as a ideal fluid. So, these things we have learned today, they are really wonderful. We are going to learn more thing in the coming classes, which I told Newtonian, non-Newtonian, same examples are given. Example you can see here, air, water, oil, gasoline, alcohol, kerosene, benzene, glycerine. So, a liquid or a fluid obeys Newton's law of viscosity is a Newtonian fluid. A liquid or a fluid or a gas does not obey is a non-Newtonian fluid. Like I told, it may be a sewage, it may be a blood. This is what actually we would like to tell. So, mind it well, viscosity, we have one more term to conclude today's lecture. The kinematic viscosity is a one more term which is very important in our engineering systems. It is the ratio of dynamic viscosity to density of the liquid. I repeat, it is called nu. It is ratio of mu by rho. Nu is actually mu by rho. So, the units are centimeter square per second, which is called in CGS system as stroke. Again you may be thinking centistroke is there, answer is yes. 1 by 100th of a stroke is centistroke. What is that? It is dynamic viscosity. How it is defined? It is dynamic viscosity divided by rho m is equal to kinematic viscosity. In the SI system, we can multiply centimeter square per second into 10 to the power minus 4 to convert into kinematic viscosity. So, meter square per second. So, with this I think I stop my lecture. Today we have learned very important properties like mass density, specific volume, specific weight, specific gravity, and a very important dynamic viscosity and kinematic viscosity. Thank you very much. Hopefully we will meet again tomorrow. Be ready with your calculator. Thank you.